That was ionic bonding. Let's look at covalent bonding. The Lewis structures are going to show molecular compounds as neighboring atoms that are sharing electrons to get octets. Or the little guys just want a duet. So let's look at water and chlorine and see how these guys can share electrons to get an octet. So let's start with oxygen. How many valence electrons does oxygen have? 6. Now, I'm putting the unpaired ones on the right and the left just because I know what I'm going to do next, but you could put them on top and bottom or next to each other. It doesn't really matter. So oxygen has 6 valence electrons, and then we've got hydrogen. How many valence electrons does hydrogen have? 1. Hydrogen only has 1 electron. It's 1s1. So there's a hydrogen with 1 valence electron, and I'm going to put the other hydrogen on the other side. Because I know there's 2 hydrogens because the formula for the compound is H2O. Is this hydrogen happy? No, it only has 1 valence electron. Hydrogen's a little guy. He doesn't even want to get an octet. He would just like to get a duet. He would like to look like helium. So he needs 1 electron. And this hydrogen needs 1 electron. And so these guys are clamoring at oxygen, please, please give me an electron. And oxygen's like, no way. I need more electrons. I am not giving you little pipsqueaks my electrons. That's going to make things worse for me. I want your electron. And the hydrogen's like, no way, I've only got 1. I'm not giving it up. So they compromise and they decide to share. Right? So if they share the 2 electrons, when things are shared, the hydrogen says, I get to use both of those electrons. And the oxygen says, I get to use both of those electrons. So now, hydrogen is happy because he's got 2 electrons. And then we get sharing going on over here. And this hydrogen's happy because he's got the use of those 2 electrons. And the oxygen, let's do blue for that one. The oxygen is also happy because it's got 8. 2, 4, 6, 8. The shared electrons get counted for both. Right? It's like parents with children. My husband and I have 6 children. If you ask him how many children he has, he would say 6. And you ask me how many do I have? 6. So how many children are there altogether? 12. Thankfully not. There's 6. But they belong to me and they belong to him. They're shared. So these shared electrons now belong to the hydrogen and to the oxygen. So by sharing, the nonmetals get octets or duets for hydrogen. Any questions? Let's look at chlorine. How many valence electrons does a chlorine atom have? 7. So 1, 2, 3, 4, 5, 6, 7. And then let's draw another one. 1, 2, 3, 4, 5, 6, 7. Neither chlorine atom is happy. They don't have 8 valence electrons. This one cannot convince the other one to transfer an electron to her. No way. And vice versa. So they decide, well, let's share. And now this chlorine says, I have the use of 8 electrons. And the other chlorine, I have 8 electrons. And they're both happy. Chlorine forms a diatomic molecule because in doing so, it becomes more stable. It's a lower potential energy. It's like rolling to the bottom of the hill. Easy peasy. So any questions about that? Now it says identify bonding pairs and lone pairs. Lone pairs are what we call non-bonding pairs. It's just shorter. Let's get a different color in here. So in water, This pair of electrons, is that forming a bond? Yeah, those are shared. So these are bonding electrons, and these are bonding electrons. And over here, those are the bonding electrons. So the bonding pairs are circled in red. Are there some that are not shared? Yeah. This pair of electrons is not shared. It's just sitting on the oxygen, and this pair is not shared. And over here in chlorine, we've got a lot of lone pairs. So those are the lone pairs in the green. Any questions? Yes?
Are those always the same ones, or do they switch? Like maybe the lone pair switch with the bonding pairs, or
Well,
they stay always like that?
There will be, for a chlorine molecule, there will be one pair of electrons that are shared.
And that's never going to change.
And the electrons that are shared will remain shared.
Okay.
You can draw the picture in different ways. The electrons don't switch out, oh, I'm shared for a while, now let's trade places. They don't do that. Once they're shared, they stay shared until the bond is broken. But you can draw them in different ways. Any other questions? So, back to the title here, single. These are called single covalent bonds because a single pair of electrons is being shared. Oops. We can also have double bonds or triple bonds. So let's look at oxygen, the diatomic molecule. So here's oxygen, an O, and we know that it has 6 valence electrons. And we'll draw another oxygen over here, and it also has 6 valence electrons. All we've got are oxygen atoms. They're going to try to get together and cooperate to get 8 valence electrons. So they can say, well, hey, let's share these electrons. Okay, it's better. Do they both have octets? No. But they both have another unpaired electron they could share. So they share that one too. Now they each have 8 valence electrons because they're sharing 2 pairs of electrons. We call that a double bond. So that's kind of an awkward drawing. We would more likely draw it like this, where there's the shared electrons. Exactly where you put these pairs of electrons doesn't matter. Just, choose top, bottom, right, and left. So I'm drawing these bonds right now as 2 dots connected. But what we usually do is we just indicate those bonds as lines. And just to be different, I'll put the electrons in some different places. But I'm starting out by drawing these as connecting the dots to help you remember that this line, this covalent bond, represents 2 electrons. The double line is 2 bonds, 2 pairs of electrons. It's a double bond. Any questions?
Same question.
Mm-hmm.
They don't change.
They don't change, no. So when they decide, okay, these 2 particular electrons are going to get shared, and we're going to share those 2 electrons, those electrons remain the shared electrons until the bond is broken.
Where is it where they do change? Like resonance or what? Is that what it's called?
Yeah, in resonance, it appears that they change, but actually it's just that they're delocalized over the whole molecule, and we'll get to that. Let's look at nitrogen. But this also illustrates why oxygen is a diatomic element. By forming this diatomic molecule, it's more stable. So chlorine did the same thing. Let's look at nitrogen. How many valence electrons does nitrogen have? 5. And put another nitrogen over here, and it also has 5. So what's going to happen here? Well, they're going to share They'll each share one electron. Okay, we're getting closer. Well, that's not quite good enough. Let's share another one. Okay, we're closer now. We each have 7, but still not quite enough. Let's share a third pair of electrons. Sharing 3 pairs of electrons is a triple bond. Question?
Well, can we do the same thing for phosphorus? Like, why is it that nitrogen is a diatomic?
That's a good question. Nitrogen is a diatomic molecule, and yet phosphorus is not. I think that has a lot to do with the size of phosphorus being larger. What we do see with phosphorus is it actually forms, I think it was P4 and P6. There's actually 2 different molecules that phosphorus forms, but it doesn't tend to form diatomic molecules.
So that applies either with like oxygen as well, since sulfur or selenium is bigger?
Yeah, sulfur is larger. And sulfur, just like phosphorus, there's a couple of different types of molecules that it forms, but it doesn't form the diatomic ones.
Those 4, right? Phosphorus, sulfur, and whatever that is,
Arsenic is a semi-metal, and I don't think it forms molecules at all, and I don't know that selenium does either much. The other difference between nitrogen and oxygen as a group with phosphorus and sulfur are solids at room temperature, and nitrogen and oxygen are gases. That may have something to do with it as well.
No, because I remember that those 4 form like a group of some kind.
Well, there's some tricks you can do with polyatomic ions and their charges and formulas by drawing blocks in the periodic table.
I think it's like a phosphate and a sulfate. And
Yeah,
a different amount of oxygen.
Well, phosphate and sulfate have different amounts of oxygen, the same amount of oxygen, but different charges. So if you can remember that pattern thing, that's great. I can't remember it. I just memorized them. So I think it's easier, but whatever's easiest for you is what you should do. So this is a triple bond, and normally we would draw it like this, the nitrogen and the other nitrogen, and indicate the triple bond as 3 lines, each line representing 2 electrons, and then each has a lone pair. So this nitrogen molecule has 3 bonding pairs, and each nitrogen has 1 lone pair of electrons. So this is me, and this is my husband. We have 6 children shared between us, so that means we have a triple bond, right? You can find chemistry stuff anywhere. Covalent bonding models in reality. Make sure I didn't skip one. I didn't. So one of the things that models can do, like the Lewis model, is it can predict, is this a stable molecule? A stable molecule will have an octet for all of its atoms, or a duet for hydrogen. So we already did water. Let's just draw it again. So water ended up with a single bond between the oxygen and the hydrogen, and then the oxygen had 2 lone pairs. But each of the hydrogens has a duet of electrons, and the oxygen has an octet of electrons. You see that? We look at this oxygen. You count the line as 2, 2, 4, 6, 8. Octet. The hydrogen has 2. Hydrogen is happy with 1 covalent bond. Very easy to please. What if we make H3O? Well, you take this and we're going to add a hydrogen to it. Oops. So if we throw, I did it again. It's trickier than you think. So if we throw another hydrogen in there, well, what could we do? Well, we could make a bond here, and that would make this hydrogen happy. Is this oxygen happy, though? No. It's got 9 electrons now. Is that going to be stable? Nope. Oxygen needs an octet. So Lewis structure predicts that water will be stable and H3O will be unstable. And that's true. What about H3O plus? How would we get the positive charge? Lose an electron. So we already have H3O here. If we lose an electron, if we get rid of that one, now this is going to have a charge on it, a plus charge. Does the oxygen have an octet now? It does. 2, 4, 6, 8. Each of the hydrogens has a duet. It is predicted that that is stable, and it is. What about H2O2? Do you know what that is? Hydrogen peroxide. Well, we've got hydrogen and oxygen and oxygen and hydrogen. Each of the hydrogens has 1 valence electron. Each of the oxygens has 6. So hydrogen and oxygen can share one here, and hydrogen and oxygen can share one there. Both of the hydrogens are happy now. And if we share an electron between the 2 oxygens are also happy. 2, 4, 6, 8. 2, 4, 6, 8. 8 valence electrons, each for the oxygens, 2 for each of the hydrogens. That should be stable, and it is. Any questions? Yes?
With the hydronium ion with that plus charge,
Mm-hmm.
I wonder if back in 3A they were talking about the similarities between the hydronium ion and just the hydrogen ion.
Mm-hmm.
I never understood that.
Okay.
How would they be similar?
That's a good question. So let's talk about that. So I'm going to draw another Lewis structure for water. So there's water. What would the Lewis structure for the hydrogen ion be? H plus. It's just going to be H with a positive charge. Hydrogen has 1 electron, and when it loses its only electron, it becomes a hydrogen ion. But if it doesn't have any electrons, all it is a nucleus. And the only thing it has in its nucleus is 1 stinking little proton. So the hydrogen ion is really a bare proton. This is like a newborn baby. Do you see newborn babies running around on the sidewalks? No, they're too tiny and helpless. You see them being carried around by grown-ups, right? So this hydrogen ion is very unhappy, very lonely. And what it can do is it looks over here and it's like, ooh, on that oxygen, there's 2 lone pairs. Maybe that oxygen would share 2 electrons with me. So he goes over here, and the oxygen is a very generous atom. And, oh, sure. And so we get this situation where the oxygen is sharing 2 of its electrons. Don't want to think about that. 2 of its electrons with the hydrogen. We'll learn later that's called a coordinate covalent bond, where both of the shared electrons come from 1 atom. But this is more stable. So the confusion is that we often, in chemistry, write H plus in chemical equations, because writing the H3O plus means that we have to stick a water in there later, and it makes balancing the equations and stuff just a little more complicated. So we'll often write H plus, but we understand that in an aqueous solution, this H plus is always writing piggyback on a water molecule, because it's happier that way.
I've asked that question like 3 different times. Not in this class, but
It's a good question.
It would seem like it doesn't even ask, it just states it.
Well, yeah, they don't actually ask. But. Yeah, this is my chemistry land, and I get these little pictures. I can see these little guys running around. They talk to each other. It's like kids playing with Hot Wheel cars, right? I could never do that with my kids. They'd have the cars talking to each other. I didn't even do that very well with Barbies. But atoms, yeah. Maybe we should have named the atoms nitrogen and aluminum or something, and then it would have been fun. Any other questions? So how does Lewis structure predict the reality of covalent compounds? Well, we see that covalent bonds in Lewis structure are highly directional. Those electrons that are being shared are between those two atoms. Ionic bonds, you get the attraction in all directions with oppositely charged ions. But in a covalent bond, it's just between those two atoms in the molecule. So covalent compounds have discrete molecules. And there was a question about this on one of the earlier labs that really messed with a lot of people. Can you calculate a molecular formula for an ionic compound? No, you can't. Because ionic compounds don't have molecules. But covalent compounds have discrete molecules. So what holds the molecules together? You know, you get a beaker full of water. What's holding those discrete water molecules together? It's something called intermolecular forces. We'll learn about those. But they're much weaker than the actual bond. In order to melt an ice cube, you just have to disrupt intermolecular forces. You do not break chemical bonds. And so covalent compounds tend to have lower melting points because you don't actually have to disrupt a bond like you do with ionic compounds. So we get lower melting points. Doesn't really say this on here, but what do you think? Are these molecular compounds likely to conduct electricity? No. There's no charged particles. In order for something to conduct electricity, we have to have some provision for charge to move. And there's no charges involved here, and so we can't have conductivity.